My name is Jerin and I work for Marvell. And I've been working with DPDK for quite a long time, around eight years. And when I started DPDK, it was more x86 specific solution. Then we came in and added ARM64 support, and I was maintaining that for some time. And then started moving to some other libraries like EventDev, Graph, Trace, and I was maintaining all of that. And recently was added some of the subsystems like regexdev and mldev. So this talk is about a graph library. So in the agenda, so let's first quickly get into graph architecture overview, then DPDK graph library features, and advantage of using graph library in DPDK, a programming model, and its API walkthrough. We support different graph models. I will explain that later, but talks about different graph models are supported, and the graph library internals, how that works. And we also have some inbuilt nodes in DPDK. So just giving an overview of that. And status and the roadmap, what has been planned. So let's get into the architecture. So graph architecture basically abstracts data processing function as a node and link them together to create a complex graph to enable reusable / modular data processing functions. So that would means that like you can think like each nodes as a library. So you can somebody else can write the library for you, the node for you. Then in a given use case or a given business use case, if you want to add a pre-processing to the node or post-processing to the node, you can create another node and stitch them together and create a graph. So that's the high-level view of it. So if you see this graph, these are the different packet processing nodes. So I will explain it later. So, but in high level, this is the architecture. Now it comes to the graph library. The first thing is node is exposed as a plugin, like a function pointer scheme where in order to make it as an shared object, which just it is built as a plugin with function pointers, and it also supports out of tree nodes. That means the node does not need to be part of DPDK. It can be out of tree. DPDK also comes with inbuilt nodes for packet processing, which is part of DPDK, but people can take that as a base or write different modules, or you can use these nodes as part of the graph itself. It also has a multi-process support like other DPDK library. It was quite complex to do for this specific thing. That's why I mentioned here. Also, it has low overhead graph walk and node and queue functions to enable a framework. So we have a performance test case to figure out like what's the cost of doing an NQ and doing a graph walk, etc. It also comes with the statistics of a given node took how much time and etc. So we have dedicated slides for that. Also, it has a means to export graph as a graphis file. So basically, it's like a test file, ASCII file, and there are online tools we can render this. If you see this is created through a graphis export API. Yeah, we do have a different graph walk model, so I will explain that later in the slide. Now, getting into the advantage of using DPDK, graph in DPDK is that we all know the memory latency is the enemy for high-speed packet processing, right? So moving similar packet processing code to a specific node will help you to reduce I-cache and D-cache misses. For example, if you are making an IPv4 lookup load, then you can assume that all the packet, it's an IPv4 packet. So you don't need to have if conditions in per packet. So it's like you get an IPv4 packet and can go through that. So the I-cache should be warm, and so that's the usage of it. And it basically exploits the probability that most packet will follow the same nodes in the graph. So typically in the internet traffic, if you take a burst of 32 packets, most likely it follow the similar flow so that it lands up in the same node. And this also helps to do a lot of SIMD processing because it's a node and you are doing a packet processing on the similar functionality on the given node. So yeah, so you can use the SIMD instructions to process 4 packets or 8 packets or 16 packets at a time. So so once you need to have a lot of if conditions, then SIMD concept don't really work. So in the node concept, like you know that it's all packet belongs to the same processing, so I can go over by 4 by them or 8 by them or 16 by them. This also allows consumers to reuse the nodes, like DPDK currently give an inbuilt nodes. So these nodes, they can be part of their business use case as is. And if they want to do a pre and post processing of that function, they can add a node before and after that, right? So they can reusable standard nodes, we can get it. Or if somebody else is creating an out of tree module and after tree nodes and they want to share, then that also can be used by other party. Also, it plays another extent where certain hardware features like IPsec, for example, right? Inline IPsec, some hardware we have a native support for doing inline IPsec, and some hardware it needs to be done in software, right? In such cases, the user can create the graph, right, which will have an IPsec node, and based on the platform or based on the architecture, based on the hardware capability, in slow path we can form the graph, and in the cases where it's implemented in hardware, that node can be a simple nope, right? So you can completely skip that, right? So, but it gives a means for end user to express what they need, and based on the platform and architecture, we can wire the nodes in a different way as based on the capability. And yeah, this frameworks basically use void star to move the packet pointers. So it's not dependent on a specific format, like VPP has a VLib. So, but this is void star, but we can typecast to embuff or assign to embuff and start using. So yes, if we start using embuff, then the conversion between embuff to another format, it's not needed. So that's one advantage of having native graph support in DPDK. Then let's switch the gear to the programming model and API walkthrough. Right. So this section I will go through the APIs, how to use it, and the programming model of it. This side is too crowded, but basically this talks about the anatomy of a node, right, and what a node consists of, right? So basically the green block, it's a process function. Basically this is a fast path function which defines the personality of a node, meaning what it's going to do in when it goes through a graph work. Like if it is an IPv4 lookup node, then it's going to do a packet lookup, right? So that's the process function. And each process function has a context memory, which is a scratch pad memory for that process. So this will hold the user area or context area of this thing. This is like 16-byte fast path area. If 16 byte is not enough for a node, you can use pointer and point them to another thing. So if, for example, if you are using an IPv4 lookup, then and it's implemented based on LPM, right? The tables pointer will be stored here, so that when packet comes in, the table lookup will be using the table object and get it there, right? So this object is for that. And init, it's a callback, will be called when the graph is created. So basically in this place, like if you see a driver point of view, you have init and fini, right? So init, you can do the initialization. So if you are creating a IPv4 table lookup, then the table will be created at this point. That's this, and fini is a counterpart of that. And now, yeah, and each node has a name. So this is useful for, like, once you have the nodes, and this name is used to connect them and create a graph, right? So and it works with the regex expression. Like if you have a node like IPv4 lookup, IPv4 rewrite, so that just giving an IPv4 star, all the nodes which is starting from IPv4 will be part of the graph, right? So it's name-based lookup. And there are utility functions to get the ID from name, things like that. And in graph theory, so node is connecting to the downstream nodes. We call as an edges in graph theory. So, so it has a number of edges where downstream nodes it connected to. And downstream nodes, nothing but it's a pointer to a node itself, meaning node type itself. That's is pointing to another node. So this is high level an anatomy of a node. Now, in order to explain the APIs and the programming model, I just created a very rudimentary graph just to showcase an example how the API can be used. So in this example, like there is a producer node and it's connected to process 2 and process 1. There is a concept of cloning, so I will explain that. Because of that, I have a clone node. So blue ones are the downstream nodes of a producer, and process 1 is connected to process 3 and process 4. And process 1 is cloned of process 1 and 1 underscore cloned is a clone of process 1. Because of that, it has the same attributes. And process 2 is just connecting to process 3. So there is nothing magic about this. They just put some diagram to explain how this is work. Okay, so now let's zoom into the producer. So this slide morally explains, trying to focus on like how to register a node and how to move a data point is from one node to another, right? So first thing is like, so the we need to, the RT node register gives an ops for different callbacks like process, init, and other things, so which will be get registered. So this is the part of registering a node. Now, node will have a name. That's where we use for taking this node name and connecting to the graph, right? So that's the node name. Process I will explain later. Init we discussed earlier. In this thing, there is a flag. We have one flag, right? Only one flag is there now, but that flag is called source. Basically, in the given graph, the graph walks start from a source graph, right? In this case, the producer don't have any upstream node. It's a first node, right? So this one, we mark it as a source for enabling graph work. And we call this as an intermediate node, and this is a final nodes. But yeah, so we don't need to mark intermediate and final one. Only source one you need to mark it as this is the beginning of the node to start. Now, in this example, I have a init function. There is nothing. It's whatever I started with my underscore is just a namespace to say that it's not part of graph library. But so the node.context or arrow.context is the 16-byte user area. It's free for node writer to write whatever it's there. So I'm just initializing it. And yeah, so now if we go to the process function where when a producer is get invoked, right, what it's going to do, right? So this slide, I'm just trying to showcase two things. One is number of edges dictate like what are the downstream edges which is connected to the node, right? In this case, it will come as a 3. So that's one thing too important to know. And other thing is the node NQ / underscore X1, X2, X4 APIs. These are the APIs to NQ to the downstream node. So if you see this case, I'm just allocating a packet and pushing the mbuff / the mbuffs to the each nodes, right? And I'm just filling 32. The burst size is 256, but it's configurable. Yeah, pushing 256 bytes here, pushing 256 bytes here, just to make initial thing ready. So yeah, two things to highlight here. So one is the registration API and the means to push the mbuff / data pointers to the downstream. The NQ is like one way of doing it. In coming slides, I will explain other ways to do it. So that's one thing. So moving to the next slide. Yeah, in this thing, so we did the producer. Now zooming on to the process one, right? So I will explain two things concept here. One is static node linking, right? In earlier case, we simply registered it. Now we need to establish how and what would be the downstream nodes for process one, right? So this case where we know that upfront that process 3 and process 4 is connected to this thing. So that's one thing. So if you see the registration function, we'll give number of edges as 2, which is process 3 and process 4, and next nodes as just string. So that's where string is useful to represent a node, right? So this slide explains a means for enabling a static connection between one node to another. Now, yeah, so now other process function, when you zoom in, it's another example. In previous slide, we used the expand NQ API. This is another scheme of NQing mbuff / data pointers to the downstream queue. So in this case, like producer, last slide, we pushed that thing through X1. So packet is here now, and its process 1 is being called. In this thing, like what I'm doing, simply processing all that packet. It's a rudimentary process function, but it will be, in real life, it will be much complicated than things. Especially you need to use SIMD and other thing. But for explanation sake, I'm just making it as very simple. So just process the packet, and in this case, there is an API called RT node next stream get. Basically, with this thing, you can get process 3's object hold where the packet, the data pointer needs to sit, right? So what I'm doing here is I'm getting the object, the memory area for 3 and 4, right? And I'm going through the object, like what it's been passed to process 1, and I'm checking that is belong to process 3 or process 4. Since I got the process 3 memory at this point, right, I'm simply adding the object which came through input to this, and just to add to that. Since it has only 2 nodes, downstream node, it's very simple to express like this, but in real life, it will be much complicated than this. But short story. Yeah, so with this scheme, like the process 3's and process 4's, the data pointer memory will be filled with what needs to be processed further. As a counter of get function, there is a put function. Basically, it will tell actually like how much data pointer / mbuff we put in node process 3 and process 4. And just return number of objects is total be processed. So that's it. And this thing I'm mostly focusing on 2 things. One is a concept called cloning. So the cloning of a node is basically the use case where like if you are doing an RX burst of packet, right, then it may happen that like the process function will be almost similar because reading from port 0 or port 1 or Q0, Q1 does not much change anything on the process function for the RX burst cases. So basically, cloned one will help you. Like you can clone an existing RX burst function, and you can just change the port and QID to that thing. So the process function will remain same. Typically, it will change the context area so that it can pull from a different port/Q pair. Right? It's just changing the context, but the process function remains same. So in order to clone a packet, in order to clone a node, it's simple. Just yes, in this case, process one with a node from name, you can get the node ID. Basically, it's you got the node ID of a process one, and simply clone that. And so we give a process one node ID and the name of the postfix of that name. So process underscore one is come from the parent node, and cloned will be appended, and the final name become a process one underscore cloned. So this is a cloning concept. And another operation I would like to add is like in the last slide, we are able to statically link it because we know the things in upfront. Assume like the case where in this case, we don't know what will be the connection to process 2, process 1, and process 3. So this linking you can do at runtime. You don't need to express while creating the node. So for doing so, we'll just give the name, and this case, like I created a name string array with downstream nodes, and I got the process ID. It's not producer node ID from the producer node name, and there is an APIs to manipulate the edges. So starting from RT node underscore edge. In this case, I'm simply using update. Update is nothing but this is offset 0 because I know that first edge is process 1, and next nodes is the string. So and number of edges we need to connect, right? So with this thing, dynamically. Edges will be updated and new downstream nodes can be connected. So yeah, there are counter APIs like getting an already, what are the edges already available, shrink the edges, update the edges. There are APIs start with node underscore edge will manipulate the edges. So that's pretty much on this. Now, yeah, so this is the third variant of moving the packet from one node to another node, where some cases where in this case, hypothetically, we can assume that whatever comes in process 2, you can move directly to process 3. In that case, if you see that APIs earlier, like there is an X1 variant, which is doing a load and store to that memory. There is a get and put variant where you get the memory and manually do the load and store. In this, we called as a home run, where there is a zero cost of moving objects from one node to another node, right? So this is basically doing, I have an internal details slide. Basically, in this scheme, just swapping the data pointer to enable this thing. So with this, if you're able to do the stream move, then it's a zero cost of moving a data pointers from one node to another. So typically, the way we write the fast path is like initially we assume like all the node is going to all the data pointers will move from one node to another team. And if you find a package where it's breaking that, then from there we'll start either use X1 or X1, X2, X4 variants / get and put variants. But typically we'll be assuming that best case, and if all the packet is going to the downstream node, then finally just taking the stream move and get it there. So that is basically exploiting the case where a given packet may have a similar flows. Okay, then now, yeah, so now that we've figured out the means for connecting a node to one node to another node and how to move the data between one node to another node. So with that, the graph, the nodes are connected and linked, right? Now it's time to create a graph, right? So graph creation is very simple. So there is an API called graph create, and you need to tell graph name, like which graph. So some cases like so based on the model, based on the graph model, there are cases like either a graph needs to, a instance of graph needs to run on a given worker, or meaning it needs to clone on different workers, or there are other models where multiple nodes can run on one worker. So in this case, like it's a run to completion model. So first thing is like you give the, so once you give the producer and process star, it's a regex function. So all the functions which is starting with process and producer will form a, without nodes, it will create a graph, right? So it's just saying node patterns are two patterns, and one because it's using regex star. Because of that, you can pull all the packets. Even if you don't give regex star, if you just give a process 2, then it just pulls in process 3 also. No, yeah, process 3 also, because it's linked at one point. So it's graph create will go through its all edges and pull that in and create a graph. And this case, like I just created a graph on worker 0. And if you want to create a graph on, same graph on other cores, you simply create a graph create 3 times and with a different name. So, right, that's the graph work. Okay, now that we have a graph work, then in FastPath it's simple. Like you get a, on the worker 0 FastPath, you get a object of graph from the name, which what we created last slide, my graph on worker 0. So you got the graph, right? Then FastPath is all like just do a graph work, that's it. When you do this graph work, then the process for the node process, which is already written by the node writer, will be get called, right? That's the FastPath. And now on this, get into the stats. So now we've seen that a given node will be instantiated on multiple graphs on different cores. So there should be a means where we need to aggregate the stats from different graph, right, which is running on multiple cores, right? So basically stats is getting a means for getting that. So basically here, again, the same pattern where you give a my graph on worker star, because it's just pulling the data from all the workers, right? That's where star is meant. It's a regex pattern. And yeah, that's it. Then you create a stats object, right? And just do a stat get on the stat object, right? That's it. And yeah, there is a default function which spit out the graph output like this. But this can be overridden, and there are you can have your own format what you like, but default will look like this. So in this thing, it will explain what are the nodes which we created, and number of times the process function is called, and how many objects it's processed. Real account I'll explain later, and this is like object. What's the burst size is able to achieve, right? Right. And it's like millions of it's packets it's able to process, right? So it's like, yeah, this is just a dummy nodes. Because of that, it's getting so like 3,000 million packets. But yeah, and it's then it's going to spit out like the amount of cycles, CPU cycle to process one packet, right? Yeah, so this would be very useful to debug and understand what's going on in the system and optimize, right? Yeah, that's pretty much it in terms of the APIs. I think we gone through the node registration, how to create the graph, how to walk through it, and how to see the stats, right? So now getting to another subject called graph walk models. So when I initially created the library, we had run to completion model where in a given graph that we have a number of nodes. So each nodes will be part of each core, and you will create an instance of those graphs to the multiple cores. So in this thing, it's like just a run to completion node 0 will move to downstream node, and nodes will go to that. It's all in same core. Recently, Intel proposed another graph walk model. It's called multi-core dispatch. In this thing, it gives more flexibility, but with a little performance overhead, where a node 0 can be on one core and another node can be on other core, right? And in that current scheme, it's using a ring for moving the data between one core to another core. In the run to completion, it's just a circular buffer, and it's just it does not use a multi-producer or single producer RT ring kind of a thing. But this gives a flexibility on where the node needs to be there. But the good part is the process function on the node is agnostic to the graph walk model, where once you write the node based on the walk model, the model graph model, it can deploy on either this scenario, run to completion scenario, or the multi-core dispatch scenario. So that way, you don't need to rewrite the business logic of the node, right? So that's the good part. This thing. This is more like internals of graph work. Typically, you don't need to know this thing, but I'm trying to put this thing in case, like, if you want to debug what's going on and how to improve the performance, kind of a situation, right? So the graph object, it's a memory layout of graph object, right? And I will start, and if you see the graph object, you have a header. There is a fence to see that memory corruption or not. Circular buffer will come to the last, and an array of number of nodes of part of this thing. And if you zoom in one node in, right, again, there is a fence to see there's a memory corruption and slow path area. Context memory, we talked about the 16-byte area that is specific to the node, and fast path area, which has the ops like process, init, and other thing. And set of downstream node pointer, number of edges backed by that. Then the most important thing is object memory. So basically, a node is hosting, like, the parent node is the one is going to put the data pointers to this thing. So when we call X1 API, basically, when we talked earlier, it's going to put the memory, the data pointers to this location, right? And when we had another API, get and put versions, right? That is nothing but giving this memories. And we also have a stream move API, right? In that case, what is happening is this object memories got swapped with another thing. That's where the stream move kind of API with zero cost, you can move the thing. So those the concept. And then this other thing is the circular buffer. So when a graph is created, initially it will be filled with the source node. That's where we need a flag. I was explaining it earlier. And here we are using offset instead of pointer. So if you use offset, then the cache locality will be good, and it will be size will be less. And since the nodes are part of the graph, everything will be offsetted from the graph, right? Graph is the base address, and everything will work with index. That's one reason why we are able to properly do with multiprocess. So it's all work with offsets. And initially, source will be filled by the graph create. Then graph walk is like take the first source node, and it's going to emit certain nodes back, right? So those things will be added to the circular buffer. Like that, node 1 is going to add another thing. Then once source nodes are over, whichever is emitted by the source node, right, those nodes will go on, right, till it finds the end of the graph. So we use it as a circular buffer because it's performance effective and we can save a lot of memory. Because once you process the node 0, there is no need for the node 0 thing back, right? Because it's been processed like that. Yeah, that's more on the graph. And now this just slides talk about what is the internal nodes which is already available in the DPDK. And the status more or less. So yeah, so the graph library was upstreamed in 3 years back, and run to completion also came along with that. We have a test suite which is also came along with that. There is a perform test suite to figure out the performance, and there is an example L3 forward graph application. It's a L3 forward graph version of L3 forward, and actually we are seeing 5% better performance than the actual L3 forward. So this is using inbuilt nodes and to form the L3 forward. The multi-core dispatch model pushed by Intel in last release. We are also planning to push more scalable graph test application because we are adding a new inbuilt node. So L3 forward is not enough. L3 forward graph is not enough to test it. So this is a review in mailing list, and this is an ID. And I see CNDP, an open source project, adapted the graph library, and this is the link for that. The sad part is like they kind of forked the DPDK, but this is the fundamental block. They are using it for all protocol processing. Yeah, it comes to the inbuilt node. Yeah, so we have following input nodes, which is already part of that. In the first release, we have all the basic nodes to enable the L3 forward. Later, we added a kernel TX and RX just for exception path handling, and IPv4 UDP, IPv4 reassembly. It's been pushed to the mailing. It's in target for this release. And these are the nodes we think we are planning to do it later, but it's not committed. So that's pretty much it, and open for Q&A. And this is the link for the programming gate.
Thank you very much. I had one question before the next person, because I'm here. Does this use the event dev?
No, no.
Okay.
So we have a plan to use even, so there is a graph model, right? So that we can plumb in event dev also if needed. Yeah.
Thank you. Other question? Other question?
Hey, Jerin. Thanks for the presentation. Nice one. One quick question about multi-core model status. Is it possible to have multi-core and multi-process together? Let's say, so one node in one process and second node in a different process on different core.
Yeah, it's possible because graph, as I said earlier, like we're creating a graph memory and which is cloning into another one. So yeah, it's possible.
Okay, cool. Thank you.
Yeah. Is it possible to accelerate some processing with some hardware accelerator?
Yeah. So there's two things, right? One, if there are like checksum offload, which are part of ETH dev, you can use those APIs. Or the cases where, like I was explaining earlier, like, so for example, if you want to do an inline IPsec kind of a situation where some hardwares, it's already, it's part of the pipeline itself, right? So when you create a graph, you can make that as a NOP, right? And the cases where it needs to be done in software, you can pull in a software node.
Okay, that's the responsibility of the application to find the right accelerator.
No, so based on the capability of the given platform, right, we can, while graph creation time, it can figure out whether to have that node or not.